Welcome to part 2 of Analytical Geometry, and for this first video we're going to look at a bit of an introduction and then a couple of examples given 2 points, and then the next video we'll look at 2 examples where we're given 1 point and some other information. So let's head into it. So our introduction here, maybe I can be out of the way here. We've got 3 kind of general formulae given to us for straight lines. Y equals mx plus c. That's the one we're going to use most of the time. And then we've got y minus y1 equals mx minus x1. You know, if you're given the coordinates of a point, that may or may not be useful. And then this final version over here, which is if you're given the 2 intercepts. I was going to say the 2 x-intercepts. That wouldn't make much sense at all. So out of these 3, we really only going to use this top one, but note that there are others that are of interest too. We're not going to use any of them, to be honest, but they're there. So yeah. Okay, so 2 examples. First example, determine the equation of the line through 1, 2, and minus 1, 3. And you'll see what I've got over here is just a little set of x-axes so that we can draw and get a sense of what this line will look like. So if we've got 1, 2, 1, 2, then there's one of the points on the line, and minus 1, 3, there's another point on the line. So you've done straight lines before, I know, so this is mostly revision. So we've got a line here. We know that our general form of a line is y equals mx plus c for any straight line function. So it looks like our y-intercept is somewhere over here, give or take 2.5. Don't want to say exactly there, although maybe by symmetry and other aspects you can see what it is. We know that the gradient here is in this direction, so we're going that way. So going that way, which means that it's a negative gradient, so we expect our m to be negative. And let me just put these coordinates in here. I think it's easier to work with. 1, 2. Okay. So with that in mind, let's work out our gradient, and we did this in the previous video quite a bit. We went m is rise over run, and just a reminder to hit pause as and when you need to, or just let it run as you do the example. And m is rise over run, so let's just go from left to right. I find that a bit easier, left to right. So from minus 1 to 1, we've gone across by 2, and from 3 to 2, we've gone down by 1, so our gradient's negative a half. That fits in with our thinking that it should be negative. Remember, you can use that whole y2 minus y1 option if you want to, but I think it's easier just to think, how far did you run, how far did you rise? Okay, so y equals minus a half x plus c. Now, there are 2 options to find our y-intercept. I'm going to do a more conceptual approach first, and then, well, maybe not more conceptual, but just a visual one on the graph, and then look for a substitution method. So if we know that our gradient is negative a half, it means that for every 1 step across, we're going down by a half. So for here, if we've gone across by 1, we must have gone down by a half, which means we can easily see what those coordinates are, because if we've gone from minus 1 to 0 and we've gone down by a half from 3, it means we must be at 2.5. And we could have done it backwards from this second point here. So if we've gone across this way by 1, well, we must have gone up by a half. So from 2, if we go up by a half, we get to 2.5. So that actually I think is quite easy. We just go y equals minus a half x plus 2.5, 5 over 2, 2.5, whichever one you prefer. And that was quite easy. Our kind of default that's always going to work, though, is just substitute a value in. So we've got y equals minus a half x plus c. Let's substitute this second point, the positive. I think it's easier to use that. So the y value is 2 equals minus a half, 1 plus c. And now we've got a little equation to solve. And if we add a half to both sides, we get 2.5. So it amounts to the same thing, but just useful to be able to have both in our back pocket. Okay, one more example, and let's see how we go. Determine the equation of the line through 4, 0, and 0, minus 3. Okay, so again, I've got a little Cartesian plane. If you didn't, you could just draw quite a rough one. It doesn't have to be exact, but it just gives us a sense. So here we've got 4, 0. I'm a big fan of writing out full coordinates, not just 4, but 4, 0. And over here, we've got our second point, 0, minus 3. So our very straight line that goes through those points, that was pretty straight. Let me move out of the way. Let's just have a re-look at that straight line. Oof, let's just look at that. Sometimes I like to just appreciate things. Okay, so let's get back to where we were. So we've got this straight line. We know the gradient's positive. We can see that. So if we know that y equals mx plus c for any straight line function, well, we know that we can work out our gradient. M equals rise over run. And in this case, we're running by 4 and... we're running by 4 and rising by 3. So running by 4, rising by 3. So y equals 3 over 4x plus c. But what's our y-intercept? Well, it's minus 3. So we're kind of given c. So we can just go minus 3, done. No need to substitute, no need to think about gradients. There it is. Yeah, one other thing just to remind ourselves over here as part of our introduction really is, if we've got a horizontal line, then that line's going to go like this. We already said in our previous video that the gradient must be 0. So if we have certain points on this straight line, the y value is never going to change because it's never going up or down. So we might have y equals, if this is k, that will also be k. So y equals k will be our general form. Because remember, it will be like y equals mx plus c. Well, 0 times x is 0. So we'll just have y equals whatever that value of k is. And then the other line that may be interesting is a vertical line. And in this case, the line would go like that. Now, we already said in a previous video that our gradient here is undefined. I don't want to say equals undefined. That feels a bit strange. Is undefined. So if we look at these points here, the thing that's not changing here is the x value. If this is n, this will also be n, even if the y values change. So in this case, we'll have x equals some sort of constant. Now, just a quick note on this, we cannot write in the form y equals mx plus c. This is not a function, so we'll always say that any straight line function can be written as y equals mx plus c, but this is not a function. Okay, let's leave it at that. I'll see you in the next video where we'll get given 1 point and just a little bit of other information.